Hi everyone, I'm Yohan from Yonsei University. Today I'm going to present our research on site semantic mapping and waypoint planning for autonomous area bridge monitoring. This is our content. Let me start by explaining why we did this research. Recently, drones have emerged as a powerful tool for bridge inspection. The common approach to drone-based bridge inspection is manual operation. But this method has several challenges. The quality of the inspection data depends on the pilot's skill and experience. And it also relies on the pilot's limited field of view that makes inspection difficult and unsafe. That's why autonomous navigation is becoming more and more popular. In fact, many researchers have already made great progress in this field. Most of them use pre-existing models such as satellite maps, BIM, or point cloud. Using pre-existing models is effective because it allows for stable and consistent path planning. However, this approach is not always applicable in practice. It's hard to apply when inspecting aging bridges without pre-existing models. It also doesn't work well when the bridge or its surroundings have changed. To address this, we propose a new system that works on-site in real time without relying on any pre-existing models. Our system has three main stages. First, deep learning-based image segmentation. Second, semantic mapping with sensor fusion. And third, waypoint generation from the semantic map. To inspect the bridge automatically, the drone first needs to know what to inspect. However, the challenge is that real-time 3D segmentation is too heavy for the drone's onboard computer. To overcome this, we use 2D image segmentation instead. YOLOVA Nano is lightweight and fast model. It processes images in just 10 milliseconds per frame. This allows the system to quickly detect superstructure and substructure. Even though the drone can detect bridge components in images, that's not enough. To plan where to fly, the drone needs to know where those components are in 3D space. To do this, we project the 3D LiDAR points onto the 2D images, assign the segmentation result to the projected points. Then we use the labeled 3D point cloud for mapping. For this work, we calibrate the camera and the LiDAR, and then match the images and point cloud using timestamp. Finally, we apply LiDAR inertial SLAM to build a real-time 3D map. This map is both geometrically accurate and semantically meaningful. The next step is to plan where the drone should fly to inspect the bridge. First, we use Landsat algorithm to extract vertical planes from the points. In use to find the boundaries of the bridge. Next, we create XY histograms based on the distribution of superstructure and substructure. We find empty spaces around the structures and define the X and Y coordinates for waypoints. Then we add Z coordinates by considering the height of the bridge. With this, the drone can follow the path that covers the bridge surface. We use the DJI drone equipped with a Velodyne LiDAR and Interloop mini-fish. For segmentation, we started with a pre-trained YOLO model trained onto the Microsoft Coco dataset. After that, we fine-tuned the model using 1,149 training images from 3 bridges and 492 testing images from 2 bridges. For mapping, we used LeoSem algorithm that provides accurate and stable mapping and localization by combining LiDAR data and IMU measurement in real time. Our segmentation model achieved a mean average precision of 86.6%. This is a solid result for detecting both superstructure and substructure. However, there's still room for improvement, especially in making the model more robust under different conditions. To validate the effectiveness of the generated waypoints, we conducted a coverage evaluation using a complete bridgepoint cloud that was acquired through manual drone flight. We measured how many bridge points could be covered from each waypoint, considering the LiDAR sensor's field of view. The LiDAR can detect up to 100 meters, but we limited the range to 10 meters to avoid overestimating the system's performance. Coverage was calculated using a voxel-based approach. The space was divided into 0.5 meter voxels, and we used ray casting to check the visibility of each voxel from the waypoints. If the line of sight was blocked by occlusions, that area was considered not covered. For Bridge 1, we generated 144 waypoints, covering about 41% of the bridge points. For Bridge 2, we generated 113 waypoints, covering about 30%. These coverage numbers may look small, but they were calculated based on data collected only from one side of the bridge. The goal was to verify whether the system can generate an effective initial path when the drone is just starting its flight. Considering the width of the bridge, this coverage is appropriate for initial exploration. The execution time analysis shows that our system is fast enough for on-site processing. Image segmentation takes only about 10 milliseconds per frame. Point cloud processing takes about 1 second per frame. And waypoint generation is completed in around 3 seconds. This demonstrates that the system can support timely and autonomous bridge inspection on-site. While the results are promising, there are still a few challenges. First, the current approach uses the segmentation from a single closest image to assign labels to the point cloud. If that image is inaccurate, it can cause errors in the 3D map. To solve this, we plan to use multiple frames. We will assign labels only when the same class is consistently detected across several frames. Second, the waypoint generation process also needs improvement. In this study, we generated waypoints using 2D histograms. While this worked for creating an initial path, it has limitations because 2D representations can't fully capture the complex shapes of real bridges. In the future, we plan to generate waypoints directly in 3D space and aim to make the process dynamic so the system can continuously update flight paths in real time. Finally, we need to test the system on a wider variety of bridge types and environments. In this study, we developed an on-site, real-time, and model-free system for autonomous drone-based bridge inspection. Our system delivered fast segmentation in 3D space. It generated meaningful initial waypoints, and it completed the entire process in just 4 seconds. What's important is that we focus on integration of existing techniques. We combine the existing techniques into a single unified system designed specifically for bridge inspection. This integrated system addressed the key challenges: the need for on-site and real-time adaptability, and the fact that most aging bridges don't have pre-existing 3D models. Through this work, we've taken a step forward in making drone-based bridge inspection more autonomous, more efficient, and more field-ready. This is end of my presentation. Thank you for listening.